So today we have Chris Rogers. He's with over 25 years of experience running embedded systems, wireless communications, and algorithm development businesses. And Chris has led high caliber teams at companies ranging from Intel to startups. And he focuses on building and supporting teams capable of bringing cutting edge technologies to reality, delivering results and customer value quickly. And we know right now he's the CEO of SensiML. And tonight he will gonna create IoT edge AI code for 32-bit down to 8-bit MCUs. So Chris, the stage is yours.
Great. Thank you very much, Rosina. And thanks everyone for your time and for the tinyML Foundation to allow us an opportunity to talk here. So for those who may not know SensiML, we'll provide a brief of introduction of our tools. And for those that are familiar with us, I think the latest information here that we'll share is the relatively recent advent of optimizations that allow us to scale down truly small. So tiniest of tiny, we now have the ability to support ML models down to 8-bit MCUs for true scalability. So, stepping back a bit, in terms of the opportunities in tinyML and how AI tools can bring a level of sophistication to allow developers to quickly and efficiently generate valid code that can run on the edge. There's really two sort of vectors here that are a challenge, right? One is from the hardware standpoint, we kind of started from AI being a cloud-centric or very compute-intensive HPC type application, and with frameworks like TensorFlow we're all familiar with. And then down to the tinyML realm that this foundation and group is focused on. The other vector is, of course, the expertise, which some of the previous presenters had highlighted as well, is that many of, or I would say a great majority of embedded developers don't come from this space because obviously ML has been the realm of HPC and cloud and data center. So those skill sets take a while for them to sort of percolate through the other platforms where people are used to sort of traditional coding and compiler tools for generating code. So the first advance that we saw was kind of the movement of AI frameworks down into very efficient models with quantization and other simplifications and subsets of functionality that are targeted for microcontrollers, as we saw with TensorFlow Lite. And then we also saw tools that brought AI in general to non-data scientists using technologies like AutoML that can optimize and automate the search process that a human would go through based on years of experience and their unique expertise about how to configure models to get the kind of answers that they want. And instead, you bring computing power to that search and optimization process. So those kinds of tools have existed for some time. What we now see is sort of the advent of tools like SensiML that bring the convergence of AutoML and tinyML together to bring the ease of use and the ease of development of applications combined with the targeting of the smallest of hardware. And for us, the more recent announcement is the ability for us to target platforms like Microchip, for instance, is one we've been working with quite closely to bring the SensiML capability, not just to 32-bit architectures, but to 16 and even 8-bit MCUs as well. So I guess the sort of top level question that many in the tinyML world are quite familiar with is the need for edge AI in the first place, right? Why don't we create dumb sensors and just allow all the data to be processed in the cloud? And the reasons for that are that if you're just sending raw sensor data from a device, all of that data needs to be sent over the network. And as you're talking about aggregating that times, hundreds or thousands of sensors with increasingly rich, high bandwidth sensor points that are contained within these devices, then the cumulative network traffic becomes prohibitive. There are power implications as well. The transmit power that it takes for a wireless radio to convey all that information can become the biggest factor in battery consumption of the embedded target and impact battery life, usability, and make some applications unviable for those reasons. There's data security and privacy issues. There's the single point of failure of the network being sort of the key piece to allow the embedded device that's acting as the dumb sensor to be able to convey the data so that it can be subsequently analyzed. And then not to mention the round trip time of having that data remotely processed, where the actions that might be taken are local actions that would take place where the sensor data originates. So if we instead partition that workload so that the raw data sensing can be done locally and then convey events as opposed to raw data, we end up with a number of benefits where the network is only conveying very little amount of information, basically the meaningful events. The impact on transmit and receive power for the wireless radio becomes significantly less, therefore you have much longer battery life. The sensor data is local and therefore can be acted local irrespective of any network outages. And then of course the speed of being able to do that locally without incurring the round trip network impact. So taking that concept and applying it across lots of different applications beyond that security one I showed, where you're looking at audio or motion data, we can look at a variety of different things for sound translated to in events like a baby crying, or motion data to fall detection, or vibration, pressure, and current translating to predictive maintenance, or fault conditions or critical events that need to be acted on quickly. So that's sort of the bringing AutoML into the tinyML realm. The other aspect of AutoML, of course, is that the traditional way of doing this with an AI framework is you work in a coding environment much like this, and there's a very steep learning curve, as opposed to the AutoML tools are more constraint-based, where the optimization of the model and the definition of all of the pipeline from filtering to segmentation to feature engineering to classification takes place using an automated approach based on the constraints that you defined in the very simple graphical interface that doesn't require that level of machine learning expertise to implement. So, all told, the process of doing machine learning using an AutoML approach is a three-step process of curating a good data set. So there's data engineering on the front end. There's the modeling phase, which is largely automated, where it's a matter of setting the constraints for the model. And then there's the test and validation of the model subsequently to ensure that you're getting accurate results. So if you can see sort of where the challenge is, it's the aspect of just like high level language is to a compiler, a very picky and a detailed aspect of getting code to compile successfully really matters what your source code looks like. The same is true when it comes to generating well-labeled data sets for data-driven AutoML routines. So if the data is poorly constructed, you're going to get poor results out. So that kind of led us to believe that there was a gap in the ML ops aspect of tinyML AutoML, which is that a lot of the tools look at the user to import CSV data or provide very crude and rudimentary methods for users to define and label the data in a way that will give them quality output. So we invested significantly over the 10 years that we've been working on this, from the days when this was a tool that we had built in the Intel platform, to one where you have very much of a machine learning ops mindset to managing data and thinking about data in the same way that most developers think about source code and version management and validation, where we have sessions, the notion of session management for labeling, Different people can bring their own individual biases to the labeling process. So understanding some metadata beyond just the end use application to include things like who's labeling the data, providing annotation that's rich, synchronizing it with video, and providing a means for you to do version management and automate a lot of the drudgery work of labeling regions within a file allows for higher quality data to come out of the tool. And then bringing that into the AutoML engine itself allows us to give high quality models and generate better results, obviously. So the AutoML piece itself, the new update for us is that we've now optimized this in a way that allows us to scale from 32-bit down to 8-bit models. This isn't magic how we do this. In fact, the approach that is used, we'll show an example here based on a simple gesture demo that was done where we had less than 20K of flash, a little over 5K of SRAM that was used, and yet a 99% accurate model for this gesture recognition. And so, the key to this is we think of the pipeline holistically and not just limit ourselves to certain types of classification like neural networks. If you look at the full chain, we focus on certainly the classification, but also the feature transforms and feature engineering, so that if you've done sort of the separation of classes very well by picking the appropriate features in the first place, it allows you to create much simpler classifiers from the outset. And you've addressed a lot of the need for filtering and the signal pre-processing, the event triggering, and the feature transformation before you ever get to the actual inference model and the classifier itself. So all this is, part of the AutoML process that the SensiML pipeline uses to ensure that we get very efficient and condensed code. So the types of networks that we support neural networks like many of the tools, but we also support sort of the classic ML approaches that often get overlooked for reasons that really don't make a lot of sense from the standpoint that these are tried and true methods. The classic ML classifiers work quite well, particularly for a lot of time series data. So including them in the search process, things like distance-based classifiers, k-nearest neighbor, radial basis functions, support vector machines, tree-based classifiers, all of this is fair game, and part of what you want to include in your search process to come up with the most compact model that you can build. So with that, that's kind of a quick overview and update on sort of our scalability. We've worked on many different applications across different sectors, ranging from industrial, factory automation, process monitoring, predictive maintenance, to agricultural, to worker wearables, consumer and smart home, and smart building applications. We have more resources available on our website. So if you're interested to learn more, please visit that, or feel free to email us directly at info@sensiml.com. And with that, I will end and address any questions that there might be.
Yeah, thank you, Chris, for your great presentation. And now I'm going to hand it over to Evgeny for some questions.
Hi, Chris. I'm going to help with the questions, if you don't mind.
Yeah, great, Evgeny.
Yeah, so a great overview, Chris. I really enjoyed, very kind of condensed and very, very to the point. There are several questions from the audience, and I have a couple of questions too. I think at the beginning you mentioned you've been able to demonstrate 16 bits, 8 bits. Are there any kind of limits? Can you kind of go even to lower bit depths if it's practical? Obviously, going kind of down in bit depth, you're losing a little bit of resolution, but you're gaining quite a bit on the model size. Mm-hmm. Where is the sweet spot kind of from your perspective there? That's kind of question number one from the audience.
Okay. Yeah. So at the moment, our frontier has been kind of the 8-bit realm, looking at working with Microchip, for instance, on their AVR line and the former Atmel processors, and being able to provide models that can fit within 20K of flash, and use 10 to 20K worth of SRAM. Obviously, this depends on the use case. If you're talking about audio, the kinds of classifiers that you can select are different than those that you might be able to get away with for gesture recognition or motion recognition, those types of things. So your mileage will vary, and the point is that we strive to deliver a model that's best suited to the application that you're targeting.
Cool. That was one question. The other question from the audience was on data management, which I agree. When we see more and more kind of opinions that the tools are getting more mature, more kind of easy to use, more friendly to use, but the data becomes kind of the bottleneck. Mm-hmm. And you have tons of experience in this space. Are there any kind of practical guidelines or practical examples? I mean, you've done so many different use cases like predictive maintenance and so on. How much really data and the data, both data quantity and data quality, you need to really have a production quality type of model, not like a demo type of model. I mean, we saw a lot of demos people do kind of this demo, that demo, but
yeah,
I mean,
right. But
you have tons of experience. Right. Yeah, products. Yeah. What is kind of, obviously you need to go through the corner cases and kind of this type of things. Kind of from your experience, obviously data is important, but are there any kind of guidelines you could share with the audience? Kind of your rule of thumb, the SensiML rule of thumb for the data.
So we've almost like codified it into our process when we work with customers that want professional services and some guidance on how to design their applications, starting from the data collection protocol. If you don't think through in advance before you ever collect the first bit of data, sort of what are the things that are going to impact in the variance for my model, and make sure that I've captured that in some way, either controlled it or can capture it as metadata to help with model explainability. And so we typically go through a process of defining a test protocol, validating that protocol with 10 to 20 samples before we ever go into large bulk data collection, confirm that our suspicions are correct, and then iterate in phases where it's kind of a design of experiments kind of approach, right? Where if I have 6 different variables that could impact the model output, I might try to isolate as many of those and focus on 1 or 2 key vectors and understand those, and then introduce additional variables into the equation with successive phases of data collection, rather than just try to boil the ocean and capture it all at once.
Well, that's definitely a great approach, kind of to do it in iterations. But can you just give an example? Let's say I know that you've been doing doing some predictive maintenance, right? On engines.
Mm-hmm.
How much time? How many iterations do you need to do before you really deploy a kind of production quality model, especially for this mission critical type of applications? It's obviously the question is like, what is good enough, right?
Yeah, right. And it's hard for me to just say the answer is 4, right? But typically we've gotten away with doing 3 or 4 iterations where with each successive pass through the data, we understand what the next phase of data collection needs in terms of just sheer number. So rule of thumb, what is it? The student's T is statistic significance of 30. We start somewhere 30 or less samples, collect that. We look at the variance, and then we decide from there. Okay, now we need 100 more samples, or if it's something that's very defined, you may not need further, right? So it really kind of is a function of the application. Unfortunately, that you can't just give sort of one universal answer to that.
Yeah, that's fair. And I have 2 more. One from me and one from the audience. One is you and the company SensiML. You are one of the veterans of tinyML industry. Actually, and before it became tinyML, you were already doing quite a bit of work in this space. And then you show the slide with several different use cases. Kind of from your finger on the pulse of the industry, what are your kind of interpretation of most promising applications or most promising industries? So like, where do you see that tinyML is going to have most impact in this in that.
What's the killer application?
Yeah, sort of. But
that's the thing that drives us crazy, but also makes us incredibly rewarding, is that it's highly fragmented and everybody's doing everything. We've worked on chicken coughing. I didn't even know chickens coughed until we started that project. But yeah, it's a big deal in poultry farms, apparently, to understand the early signs of disease using acoustic monitoring of chickens. And so, yeah, to say that, there's one killer application, so far the space seems to defy that. But that makes it interesting. We love to see what people come up with as new uses for taking, sensor data and providing that kind of pattern recognition and insight at the edge.
No, that's great. And the very last question from the audience, Chris. People asking, and you made a point at the end that sometimes you use CNNs, which are fashionable these days, right? And sometimes you use kind of more traditional approaches like the tree-based or cascade-based or SVMs, those kind of things. Again, and I really appreciate this because I think, again, CNNs are super popular. Everyone just use them, right? TensorFlow, those kind of things.
Yeah.
Either, again, kind of from your experience and your team experience, either a rule of thumb, like how do you decide which way you're going to go, the CNN way or kind of the more traditional way?
Yeah, that's a great question, and you're right. It's not nearly as sexy to talk about a decision tree model as it is to talk about neural nets. But in some cases, that's that's what the application warrants, right? So you pick the best model. The best model is the one that fits the application, gets you the accuracy that you're looking for with the smallest amount of resources required, right? And so in some cases, that's not something terribly, exciting. It's very basic classic ML. Where we found sort of rule of thumb is audio applications tend to be ones that, using MEL filters and neural nets is sort of where we would start. And even for the search process, we would direct the search process to favor a search in that realm just based on sort of that overall understanding. Whereas things like gesture recognition, motion analysis can use statistical features with tree models or ensemble models with good results. So we do tend to kind of come into it with some bias of our own just based on history of knowing which models tend to work best for which applications and then start in that realm.
And I assume your AutoML tool does this kind of decision automatically, kind of which way to go, or it needs some kind of manual steering?
It can. If you want to do brute force and you say, hey, I know nothing about AI, just start searching. You can give it no guidance and just have it come back with what it can. If you're looking for answers quickly, obviously you can converge because that's a fairly high dimensional space to be searching across when you factor in filters, feature engineering, different segmenters, and not to mention the hyperparameters of the classifier itself. Then you can direct that search by going in and saying, filter your search process for the following, and you'll converge on an answer more quickly.
Well, thank you, Chris, and thank you for the great presentation, and thank you for staying with us late, and thank you, SensiML, for supporting tinyML community.
Yeah, thank you very much, Evgeny and Rosina, for having me, and for everyone for your time.
Yep.
We especially want to give thanks to our strategic partners, which really helped us that we can make that event possible. So we have first our executive sponsors. We have ARM, which is the Software and Hardware Foundation for tinyML. Then at Impulse, tinyML for all developers. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, end-to-end deep learning solutions for tinyML and Edge AI. And our platinum sponsors, Reality AI. They add advanced sensing to your product with Edge AI, tinyML. Then also we have Renaissance, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge. Maxim Integrated, enabling edge intelligence. Seed Studio, the IoT hardware enabler. SensiML builds smart IoT sensor devices from data. SynSense building sensing and inference hardware for ultra low power embedded mobile and edge devices. And our silver sponsors, we have Aeon Devices, Deep Light, EMSA, Green Waves, Gravity Inc., HOTG, Imagibob, Geekzo, Rixon Technology, and SAP. So we really want to thank all of our strategic sponsors who will help us. And I hope you all enjoyed it and that we see you again tomorrow. Good evening, everyone.